for this, for delta x, this one equal to 0.1 meter multiplied 25 times 10 to the minus 6. So this one is 2.56 times 10 to the minus 6 meters. That be okay? One more thing. Here we calculate this number and this number that only tell us is the magnitude of the deformation. Right? And this one, if you think about this as a chewing gum, if you stretch it in this direction, both in x and y direction, the deformation must be shrinking. So that means here, if you want to make the things complete, you better to add artificially a minus to indicate the deformation is shrinking. Keep this in mind, okay? And I try to, in the calculation, I try to disengage the sign from the numbers, from the magnitude. But in the very final step, you have to justify from the observation of the problem statement to give a appropriate sign. That be okay? And next example is to practice our Hooke's law. Any questions? Otherwise, I'm going to erase this block. And probably for you, you can, okay, let me write it out this one with you one more time. So the next example is this. For example, in between the two clamp sides, we squeeze in, for example, a rubber. Okay, and the rubber is not completely fixed to the wall, but here is certain rollers. So that means the rubber will be free to free to move along this direction. So let me call this direction is x direction. This is x and y direction. Okay. So here the roller is just simply saying there's a no constraint. They kind of free to move or free to deform in this direction. And this is elastic material. And for example, here we given the material properties. For example, Young's modulus E for this material. And here I give the dimension here. From here, let me call that is L. And furthermore, let me say the dimension is H, okay? And consider this is a three-dimensional case. So in the side view, this is front view. This is side view. So in the side view, that will be this will be y direction, this will be z directions. And the dimension here is, let me call the thickness T. So that is the setup of the material. Simply we just kind of snap material inside the upper and lower bound. And when we snap in this material, basically just enough to snap into this space. And if without any loading, that is fine. But now we are trying to give certain loading. And for example, here I apply the uniform pressure. This is called the sigma x. So simply is this. Once we snap in this material, then we try to squeeze this material from the two ends. So what you can imagine is this. This material by itself will try to expand in the other two directions. Which direction? In the z direction, but also in out of the board direction. Out of the board direction, there's no constraint. So this material is free to expand out of the board. However, this material has been constrained in this z direction. So what happened? At this moment, you should have a feeling this material will experience some kind of compression in this direction because it tried to extend vertically, but that has been constrained. Got it? Okay, but in the outer board, it's free to expand. Free to expand, that means there's no stress. Okay, free to expansion, free to deform, that means in that direction there's no stress because that's all the material free to go. So now for this example, we want to calculate the stress in y direction. Again, in the y direction, we know that this material is experiencing compression. We want to calculate how much is that compression. And then we want to know what is the change in the thickness. The change in the thickness is this. Thickness is in the outer board direction. In the outer board direction, there's no constraint, so this material is free to expand. We want to know how much that expansion is. That is this amount. Okay, so now we can, for this example, our solution is this. Let me rewrite, because that is very typically, this is a three-dimensional loading case. So that is the only equation we can go forward. So let me write it up here one more time. And here we also given the Poisson ratio, mu. This has no thermal loading, so we don't need to write the thermal loading term. From here, you can see among these equations, we can calculate how many parameters. We have 3 stress. We have 3 strain. Stress is sigma. Sigma y, sigma z. Strain is epsilon x, epsilon y, epsilon z. But here it only has 3 equations. So that means among these 6 parameters, we must identify at least 3 quantities to solve for the other 3. Otherwise, the system becomes indeterminate, and that's really a headache. I can tell you that indeterminate problems for 3-dimensional case really a headache. Okay, so let's try. The known parameters. Usually we can justify by 2 categories. One category is from the given loading at the boundaries. And then the second category is the given boundary, the given constraint. At the boundaries. Okay, so we tried from basically, in one word, the known parameters usually are created or produced or implied by the problems at the boundaries. So we look at the boundaries. For the stress, the first one is this. We know that for example, say the stress x is given, and for example, say let me use the symbols. For example, this one. For example, here let me change the symbol. Say this is the pressure, certain magnitude of the pressure P0. How about that? And that could be easier for our symbol. So they basically, for this case, the stress in the x direction, the magnitude equal to the pressure, but that is compressive. So we give a minus sign here. Okay, so this is for this one, and now for this one, we'll look at the boundaries. And these boundaries, in the y direction, the material is fixed, and no deformation is allowed. Delta y equal to 0. That is due to our constraint. That implies the strain. Strain in y directions divided by whatever the dimension is. So this implies strain in y direction equal to 0. Right? So we have checked the x direction, we have checked the y direction. So now we check into the z direction to see what we can obtain. In the z direction, the material is free to expand. Free to expand, that means, what that means?
No stress.
No stress. Okay, that is the key thing to make the difference of the human beings from chimpanzee, because you have a deduction capability. It's hard to say, but are we okay? Okay, so now we have three things, 1, 2, 3. So now we simply plug into the appropriate numbers here. The epsilon x and sigma x equal to minus p. So this one I plug in here, minus p0. And this one is minus p0. And this one is, I just introduced the numbers. And so I have utilized this one. Let me label it. And then sigma z equal to 0. So sigma z equal to 0. So that means this one equal to 0, and this one equal to 0, and this one equal to 0. Okay. The final one is epsilon y equal to 0, so this term equal to 0. So right now we have three equations. Exactly, we have only three unknowns, and we can try to solve one of those. So let me erase this part.
But how is P not known if we don't know it?
How, say that again, please.
We don't have a value for P naught, so...
We, yes, this is a certain given parameters. We just assume we know it. So basically the answer will be expressed in terms of
the
P
P
naught.
naught.
Yes.
Okay.
So right now from here you can see from the second equation, let me call it 1, 2, 3. So let me say, starting from the number 2. For equation 2, we have is 0 equal to sigma y e. Let me simplify this expression, mu times minus p now. So therefore, from here we can know that sigma y will be equal to minus mu p now. Magnitude is this, and compressive minus automatically. And then from equation 1, we can plug in, so epsilon x will be equal to minus mu e times sigma y. So I plug in the sigma y, minus mu e, sigma y is minus p. So that is mu squared p now e. So epsilon x is that big, and quantity is positive. So in the x direction, wait a minute, why?
I think you forgot the negative p naught over e. The first part?
Right there. Yeah. Oh, I forgot this one. Right? Okay, so this one should be equal to E. Let me copy my answer directly. Let me do this quickly, okay? E minus P now minus mu square P now plus, yes. So this would be E P now minus 1 plus mu square, right? Are we okay? Nu is between, as I said, is a number less than 0.5. So basically this coefficient is a negative number. And so that means the deformation or the strength in X is negative. That means shrinking. So look at this one. In X direction is shrinking. Okay, yes, we compress it, it's shrinking. Let's get this one. Then equation 3. Epsilon Z will be equal to mu minus E minus P0 plus sigma Y and minus mu minus P0 plus sigma Y equal to this one. So that will be equal to E P0 mu plus mu square. So for this one, this is the positive numbers, so epsilon Z get extended. So now we want to calculate delta T. The delta T is the change of which is the deformations in Z direction. So basically, the deformation in the Z direction, that means dimensions in the Z direction multiplied with the strength in the Z direction. So we have this one simply multiplied together. Why? Do you remember in our one-dimensional model, what we have is this. From the beginning of our chapters, we have the model is P like this. And this is our whole dimension. And I say that this is our deformation delta. So the strength equal to delta divided by L, right? So that means the deformations equal to the strain multiplied with corresponding dimensions. So right now our focus is in the Z direction. So basically I just use different symbols. We still pick up the dimension multiplied with deformation, with the strain. Okay? Okay, give it a try. And again, for using Hooke's law, the key step is here. You try to observe from the boundary conditions of the problem. Sometimes we'll go to the stress. Sometimes we'll go to the strain. And at least get the 3 pieces of information, then try to solve that kind of the algebraic equation. So we have not much left, and probably Wednesday I will introduce one more material properties, and then I will use the table to talk about the stress concentration, and that is a piece of cake. We look at the table.